So hello everyone, I am Jose Garcia, and today I'm here to talk to you with my colleague Kishore Dangudurai
What does that even mean?
on how to empower MBSE with simulation and trade studies.
So
I'm not known for being subtle.
Yeah, I'm not either.
That's good.
I did a little research.
We're getting
I
crosstalk.
came back and said, well, agile engineering refers to software development
I think this is working, but we were getting someone.
You just build it incrementally. Blows up a little. And, yeah.
Well, while they sort that out, I can talk through this. You're likely familiar with model-based systems engineering. It's the formalized application of digital models throughout the system lifecycle. Here we see a standard system engineering V diagram with the various lifecycle stages. CATIA Magic, which some of you may know as Cameo or Magic Draw, is a best-in-class MBSC software suite providing the environment to define the system architecture. And system engineers utilizing MBSC are critical for modeling the system definition, but they can only partially assess the system performance in support of decision making. So the system engineers rely on domain teams who in turn have their own models and simulations that they utilize to generate specialized technical data. Ad hoc communication and data transmission across these teams can be a source for human error and delays, multiplied via the normal continuous collaboration cycles. Data versioning control across these different levels is also a source for concern. If we could instead integrate the domain models with the system model, we could be able to directly trace and reduce reliance on ad hoc communication and makeshift data. If that sparks your curiosity, then you guys are in the right room. All right, so we're excited to share with you today this solution which can empower teams to integrate with the models and processes of other teams. The first integration that we will cover is from the perspective of systems engineers. We will embed a simulation process into system-level behavioral diagrams, extending the versatility of CATIA Magic simulation. The second integration that we'll be seeing from the perspective of a domain expert, where we will embed a SysML model into a simulation process, allowing us to directly source the SysML model for simulation parameters. Both of these integrations point directly to the models being developed and validated by the authoring teams, which eliminates the effort and potential errors from transcribing or rebuilding. With these integrations, teams can leverage expertise without tying up personnel availability. All right, so let's see a quick show of hands. Who here knows who Mark Rober is? Anyone? All right, got some hands. All right. Who's familiar with the Porch Pirate glitter bomb? Some more? All right, well, yeah, Mark Rober's the guy who made that. What's that? Yeah, he does a lot of videos, and they're all pretty interesting. And yeah, he sometimes does videos on inventions that he thinks are interesting. And this is one of those videos. If you're familiar with that, this one's about autonomous package delivery system. So it came out this year, so it's a little earlier, but you might have seen it already. And as a disclaimer, we're not sponsored by Mark Rober. We're not sponsored by any of the guys in this video, but we thought it was a really interesting case study. When we saw this video, we immediately started imagining, what challenges might exist for an MBSE project like this. That's, an autonomous package delivery. The drone itself has numerous subcomponents that will need to be designed, verified, and integrated. And the drone itself is one of a fleet of mini drones that are command and controlled, launched, and there's recovery and storage ground systems for that. The first integration topic, if you recall, will be embedding the simulation process into system-level behavioral diagrams. So the context that we're going to use for that is part of that subcomponent there for the drone, the battery pack, and showing how we can integrate some of these things together. So let's dive in. All right, on the left, we see an example of a battery module, its components and requirements. The highlighted requirement is for a max temperature. Since the system engineers are not experts on thermodynamics, they will call, email, or meet with the SME and say, hey, I'm evaluating this requirement against the system. Can you tell me if the requirement can be satisfied? The SME, in turn, might need to make some phone calls, emails, and have meetings with their teammates and say, hey, I have a battery space allocation module, Bob has the charging controller model, and Sue has the battery cooling simulation. We need to run all of these to get an answer back to the system engineer. And ultimately, they will communicate back to the system engineer and say, with the values you gave us, you do or you don't meet that requirement. this human-in-the-loop process is something that many of you are likely familiar with, and it can be slow, inefficient, and non-scalable. It introduces additional risk of human error, and it lacks data traceability. Furthermore, running this human-in-the-loop 1,000 times to optimize on the system design will have large effects on personnel availability. We can reduce these risks and increase our productivity by utilizing the 3D experience. SMEs can develop and validate model templates of their simulations at any level of fidelity and share them in 3DX with the system engineers. For this example, the SMEs are sharing again that battery space allocation module, the charging controller model, and battery cooling simulation, just as an example. The system engineers can then integrate those templates directly into the SysML model to verify requirements, leading to a decreased reliance on human-in-the-loop processes and a greater traceability and scalability. So I'll now show you how easily we can seamlessly integrate these together. Let's see if we can get this going. All right. So this Cameo diagram shows the battery module, its components and requirements, as we saw earlier, the system definition. We will create a parametric diagram where we can simply drag and drop the SME-created simulation templates from the 3DX platform just on a web browser and drop those into Cameo. And once we do that, you'll see that Cameo automatically will read the input and output parameters, and we will connect those associated parameters with the battery system model and the ports of the templates. We'll also utilize the parametric equation wizard, which you might be familiar with in Cameo, that can connect these parameters together, but of course this is manually editable and fully configurable. These connections will ultimately enable us to pass values from the SysML model directly to the template and back. Here we see an alternate approach using an activity diagram instead of a parametric diagram. Drag and drop is also supported for these types of diagrams, and we're going to run the simulation so you can see that simulation pane on the left will load the system of interest and the defined parameters. We see values for the number of batteries, number of battery cells, for example, but not for the max temperature, since that's what we're waiting to calculate. When we start the simulation, you'll see that the parameters will be read and passed onto the simulation templates, and once the template has those required inputs, it will begin executing immediately on the platform and provide an answer back to the Cameo model. Now, to recap, in this example, we want to know if the charging system design can satisfy a max temperature requirement. So once we get the answer back, we'll check to see if that answer meets the requirement. And you can see that it's already highlighted in green, meaning that the requirement that was assigned to it is already being met by this design. So let's do a quick recap of what you just saw. The system engineers developed a SysML model but needed specialized simulation data from SMEs to verify system viability in meeting a requirement. The SMEs composed and shared simulation templates from their specialized models and simulations, and the system engineers utilized those templates to leverage the subject matter expertise for as many iterations as they need without having to tie up the SME availability. The templates themselves directly document the SME data workflows, and inefficient communication loops have been removed. To talk a bit more about the in-depths of the simulation templates, I'm going to pass this off to Kishore.
Thanks, Jose. All right, so let's go through how, so what Jose showed was more from the systems engineer's perspective of how this process is run. But what happened behind the scenes was there is a subject matter expert first put together that validated model template. We'll take a look at how that process is done. So first, this SME would develop and validate their models just like they do today in their workflow. They could either use ModSim 3D Experience virtual twins, or they could use their own in-house tools or external tools, and also, as you might be very well aware of, using reduced order models or FMUs to build that. Once you have it built, the next step is to compose a process. We will compose either of those tools or a chain of tools into a process, define the data or parameters that will be used and passed by it. Then there will be a small collaborative session with the systems engineer. What this is for is, if you remember Jose's video, what he showed you was dragging and dropping the template from a web browser and then clicking the parametric wizard for it to connect the system parameters automatically with the process parameters. So there is a little bit of collaboration there to say what inputs and outputs should be exposed for the systems engineer to be able to use this published template. So once that's set up, the SME would create a template, also configure to say where it would be run. Now you could set it up to run on a remote desktop, or on the systems engineer's local machine itself, depending on the tool availability, or even your high-performance compute cluster nodes as needed. Once that's set up, you would then make this template available for the systems engineer. The systems engineer, as you saw in that previous video, would drag and drop and add it to his SysML model and make that an executable model for him to run and get the results back. Let's look at how the SME put together that process. The tool or the application used here in this case is Process Composer. So Process Composer, as you will see in the screen, provides an easy drag and drop interface. As you will see on the animated GIF, it's basically dragging and dropping tools or what is called an activity block to build the workflow, creating a chain which is either a simple one-step workflow or a series of activities or series of steps tied together to follow a sequential or even a more complex branching and parallelly running activities. Once that is set up, then you would pass information between these different tools of choices that you have selected. That happens using what is called parameters. We'll look at that in detail in a little bit. And as you can see at the bottom here, you see that Process Composer provides you with a suite of adapters. What these adapters are, let's say, a step in your workflow. It could be as simple as a pre-processing or data processing step, a small script that you could run, a small calculation that you could run, or a specific tool that you would launch. So without having to manually code the whole process, you're just using this drag and drop capability to build that workflow. Just to highlight here, Process Composer has a fully open data model. As you heard before, you could either use 3DX tools itself, or you could also use your own in-house external tools to build this workflow. All right, so a few slides ago, what Jose showed us was how easily the systems engineer could leverage the SME's expertise that was captured in that shared model template. Now, what we saw was that was a single run where we estimated the maximum temperature as part of charging the battery of the drone. Now, let's say, what if we want to find the optimal configuration for the max temperature requirement? What if we have competing requirements and we want to perform a little bit of trade-off and pick what configuration meets our requirements or meets our needs best? You would typically start in today's system by building that user-defined instance table and then running through those to figure out which combination works for you. The challenge here is this is a tedious process. It's slow, sequential execution, completely ties up your client, and more importantly, does not provide you the option to do any optimization or results analysis. So the next question is, how can 3D Experience help you here? Let's send it back to Jose to look at an example, and we'll be back.
All right, thanks, Kishore. All right, as we all know, analysis in the early concept stages is critical for optimizing that system design and avoiding costly redesign later. Our second integration demo today will showcase powerful design exploration techniques leveraged to explore that design space and perform data analytics on the results generated with direct inputs from a SysML model. Our previous integration example centered on that battery subsystem, but as we mentioned, it's only a small part of a larger system, of which the drone itself, you can see the flight path there, has takeoff stages, flight, delivery, and landing just for one drone. And that drone is part of a larger fleet of vehicles that is managed by your overall package delivery system. Now, for an optimization question that we want to challenge ourselves with is, what if not just trying to optimize one drone, but trying to optimize the whole system in terms of finding the ideal location for a set of geographically distributed potential locations for delivery? So that is what we're going to focus in for the second integration. And let me tell you, as a modeler, that's a fun challenge. I kind of had fun, so I'm glad to walk you guys through this. Let's play the video here. So again, you guys are likely familiar with CATIA Magic. Here we have a BDD with a simplified view of our system definition. A particular importance for this will be the drones and the ground system hubs. And now you see the different defined state machine diagrams that capture the behavior and triggers for our system of interest. When simulated, these systems will be activated and will step through the behavior as time is progressed by the internal simulation clock. The top left is the overall package delivery system, transitioning to active when the simulation begins. The top right is the command hub, which checks orders and issues commands to the other systems. The ground system packaging and storage hubs are jointly modeled in the bottom left, where they have the pre-launch and the drone priming states. And finally, the bottom right defines the drone flight, delivery, landing, and recharging. So, as I mentioned, the command hub element is critical for distributing the signals that issue the controls for the behavior of the other systems. So in this IBD view, we're going to run the simulation and showcase how this runs. So when it first initiates, you'll see that the system check is performed to verify if all the systems are ready to go. Once they are, once an order comes in, the command hub will ping its fleet of drones to see which one's available for takeoff. Drone 1 is responding and it's available, so the order will be assigned to it. We then see that the system goes into pre-launch and priming states, after which the drone itself is launched and goes into the cruise mode. That then updates the order status to say it's processed and it's out for delivery. You can see there in the order status on the bottom right. We'll go through this iteration for a couple of these orders. And you can see that that second order was rejected because it was outside of the delivery range for this optimization problem, right? So going into the third, once the third order comes in, this one has nice little videos embedded so you can see real time what's happening. Drone 1 is already flying, so it's not available. And it'll go next to drone 2 to see if it's available, and it's good to go, it's charged, and the order will be assigned to it. Now the packaging hub will start preparing the package and load onto the drone. The drone's loaded onto its launch catapult, the wings are attached, the battery's attached, and the nose cone is put on there, and it's getting ready to go. Then drone 2 is launched, and it goes off to deliver its package. Coming back to the state machine diagram view, you can see that these are still executing depending on what's happening. The command hub there is assigning the next order, and this time it'll assign to drone 3 because drone 1 and 2 are already assigned in an order. So the pre-launch stage there at the bottom left is preparing that order, finding that inventory, again loading it onto the drone, prepping that drone for launch, putting it on the launch pad there, while the bottom right has the state machines of that drone 1 as it continues to cruise toward its delivery location. We see that drone 3 there has taken off, and it actually has the shortest distance, so it's got a nearby order, and it will complete its delivery before the other ones. So we're going to speed up the simulation as it runs through, and we will see that once it arrives at its location, it will go through its delivery states. On the top left, you'll see that it goes over, drops the package, which is parachuted down to its delivery location, and then it will return back to base. So you can see that the delivery distance is now increasing again because it's going away from that delivery location and headed back towards its hub. Once all of this is done, you can see that all our order statuses there are being updated, and drone 3 will now soon reach back to base. I think it was 9.6 kilometers. So you see that a tail hook for this specific example catches it. Once it's stopped, the ground crew comes, takes off the nose cone and the wings, puts it back into storage, and sets the battery to be recharged and put into the next iteration. So this is this basic idea, again, of the modeling of what it would take to capture the mission performance of this overall package delivery system. At the end of this simulation, we see that we have which orders were delivered, which were rejected, and importantly, what was the timing of those orders. So from my perspective, again, this was fun to build, and I'll talk to Kishore. I'll pass it off to Kishore, and he can talk more about how you can leverage this type of mission simulation and optimization.
Thank you. All right, so let's look at what we have here is a mission model, a system level mission model. And the requirement we have is how do we find, like you saw in that first screenshot of like Jose talked about, how do we find the optimal location to set up our hub? So we have, let's say, a set of 22 targets in this place where we want to deliver the particular packages. And we want to pick that optimal location for the hub so we could successfully deliver to all these locations in a timely fashion as well. So to build this, instead of using the instance table method, we're going to be looking at how we could leverage the 3D Experience platform's tools and capabilities. So the tool of choice again here is Process Composer. as you saw in the previous slide, we talked a little bit about adapter. So what we have here is the MBSE adapter, which essentially ties in Jose's system model, the mission model there. And we are going to then drive that using an optimization or DOE adapter. So there are different techniques available in the 3D Experience platform. There are 11 different design of experiments or DOE techniques available that lets you efficiently assess the design space or the trade space. 16 different optimization techniques available for you to drive design towards the desired objectives. In this case, for us to deliver the packages to all the locations or maximum amount of locations in a timely fashion. There are also some DS proprietary techniques here, which we'll talk about in a bit. We do also have Monte Carlo simulation for uncertainty quantifications, where you can introduce some uncertainties and tolerances and test the robustness of your design. One of the major advantages here is we talked about the tedious, slow process of setting up the instance table there on the other side, right? Here, this design matrix or the design space is auto-generated by the tool. So you just specify the limits of what your design space will be, and it automatically generates that design space. It also has the capability to execute in a fast and parallel fashion and execute the system model at any system level. So as we execute that, you'll see that it generates different alternatives or different configurations to see in which location we can set up the hub and how the system model or the mission model performs in this case. What now? We have generated, say, 50s or hundreds of points, and we have a lot of data. What are we going to do with this data? How do we figure out which of these data points or alternatives is going to work out best for us? To do that, we bring in results analytics. Results analytics, again, is a web-based tool. So just like how you saw the systems engineering was leveraging the SME's knowledge just by using the browser, right? There is no additional tool required. You use the browser to find the simulation template, drag and drop that into your systemal model. Similarly, again, a web-based tool for you to bring in all this data. And results analytics lets you perform or manage all that data set and perform trade-offs with the rich visualization capabilities to pick which of these alternatives that are the design configurations that you have generated meets your requirements the best. To talk a little bit more about results analytics, results analytics is the decision support tool, as I would like to call it. It collects all your analysis data sets to visualize and study to understand which works out best for you, ranks and scores these alternatives depending on the inputs that you provide, and lets you compare the performance KPIs of these designs in a single view in a side-by-side fashion. It also provides visualization capabilities for you to quickly narrow down on what will meet your requirement. A couple of things which we are not going to show in this demo, but I would like to just highlight is if you were to start working with requirements, Results Analytics has the capability to read in requirements to sort and rank these data sets, and essentially feed your learnings back into the requirements. Similarly, as we talked about a little bit earlier, FMUs, or reduced order models, is of great interest. Results Analytics does have the capability to generate and export FMUs from the data sets that's loaded in it. Okay, so I have a video here which will look at how this mission model was tied via process composer, automated driven, and we'll look at the results. Let me start playing that at first. So what we have here on the screen is called a process or a workflow. And as you can see, on the top, there is a straight line that signifies the process. The blue box underneath is an activity. And at the bottom, you see that there are different adapters provided for you to drag and drop and start building your workflow. So in this case, I'm going to take, let's say, the script adapter at first to do some pre-processing on the data. And then going to pass that to Jose's system model. Let's take a quick look at how the data is passed to the system model. And this is where I said parameters are what is used here. As you can see, what I'm providing in is the latitude and longitude, basically the coordinates of where the hub is going to be positioned. And the system model executes. Those two are passed in as input, and the system model executes to generate the order status, which, if you remember from his video, was a long string that had the complete information of what all points were, or what all targets were successfully delivered, and how long it took, and what drone delivered it, and things like that. So once I have all that information, I do have a few more adapters or tools in this case to perform some additional post-processing to generate the mission report, and also generate a plot for me to visualize and see how the delivery was. This sets up a single run. So this blue block here is a single run where the inputs are fed into the system model, run, the data is received back for the 3D experience platform to look at. Now, in our case, we want to perform a trait study. So we want to run this multiple times to figure out which alternative or which configuration is going to work out best. To do that, I'm going to bring in the optimization adapter. That's what you see on the top. So when I look further into the optimization adapter, as you can see, there are different optimization techniques. The technique I picked is the adaptive DOE. That's a DS proprietary technique. To go a little bit deeper into it, what it does is, essentially, I'm telling it I want to run 3 iterations of 20 combinations. So it's going to run 20 different, it's going to create 20 different design sets for each iteration. And as it goes from one iteration to the other, it's going to start honing in on that place where there is more successful points. We're going to define the objectives of what we want, and this technique is going to automatically hone in on the place or the location where there is more and more successful deliveries possible. All right, so to feed into that DOE, like we said, to feed into that optimization will be the design variables. So we are going to feed in the location of the hub. So I'm passing in the base latitude and longitude. And as you can see, I'm not manually feeding in the points. I'm just specifying the lower bound and the upper bound. And I'm specifying a step size. That's not mandatory. I'm specifying a step size of how narrowly I want to vary that to see where all I can specify or put the hub and see how the delivery performance is. I do have the option to specify or define some constraints as well. I've not done that here. And I'm going to set up some objectives. I'm just going to set up one objective, which is maximize the successful delivery percentage. And don't forget, like I said, there is the execute and parallel capability that's going to let you quickly run through these design points without tying down your client. All right, so the optimization run happens. There are, I think in this case, we generated about 50, 55 points. All these alternatives have been generated. What next? How do I pick which of these is going to meet my requirements best? I brought in this into results analytics. As you can see, this again is a web dashboard. And if you look at the data set on the top, the inputs are the hubs, are the base latitude and longitude, and the output is the success percent and the average delivery time. So I took that order statuses that Jose passed in, post-processed that to calculate the average delivery time per successful delivery and the overall success percentage, so number of targets that were successfully delivered. So the chart below shows the kind of your trade space, right? So how the hub location, latitude versus longitude, was varied and what range, and how what the resulting output was, how the average delivery time as well as success point ranges depending on the set of inputs that were provided. So at the bottom, I know my play bar is hiding this a little bit, but you see a set of steps at the bottom that results analytics kind of lets you walk through this in a guided fashion. So we were in the preview tab to look at the data set at first. Now we are in the define tab. The define tab, this is where we're going to define the problem definition. So I'm not going to make any changes at first. As you can see, it automatically read in from the optimization to say, hey, the objective here was to maximize the delivery percentage. You do have the option to tie in requirements here, which we're not going to show, but you do have the option to tie in requirements where results analytics will directly read the values from requirements to set up this problem. All right, so using the default setting itself, if I were to take a look at the next tab, which is the Explore tab, that lists all the alternatives or the configurations that were generated, the system automatically has flag some of those as you can see on the left-hand side. It's ranked all those to see one of those alternatives is the best configuration that you could go with. But our point here is not just to pick that one point. Our point here is to do some additional trade-offs. So let's go back into the Define tab and change our problem a little bit. Let's say I'm also interested in minimizing the average delivery time, and I want to define some constraints. I want to limit the upper threshold of the delivery time to like, say 72 minutes, and I want at least 80% success. Now you see that it immediately changed all these alternatives. The ranking has changed, the score has changed, and all these have been color-coded. So to dive deep a little bit into this color code, anything in red essentially means they are infeasible design. That means it essentially did not meet at least one of the requirements. One of the constraints was not met. So either the delivery time is more than 72 minutes, or the success rate is less than 80%. So it quickly eliminated a lot of those alternatives, saying those are not valid points for our case. You do have the capability to visualize this not just from the tabular fashion. You can also use some of the plotting capabilities. So in this case, let me switch over to the scatter plot, and let's compare the average delivery time versus success percent. So again, same visualization for you to quickly eliminate anything there if the success percent is less than 80 and time taken is more than 72 minutes. So we are essentially focusing on this green boxed area where most of our successful points or configurations are. Okay? So now we know the range where our data is, or where our points are, where we have successful configuration. Let's do a little more comparison here, side by side, right? So I'm going to eliminate anything that is infeasible, obviously. Now you have two more color codes left there, white and green. Green are what the system thinks is the best alternatives considering the criteria that I have specified for it. Anything in white still meets all the requirements, but one of the items in green beats that white color alternative. That's why that's color coded in white. So I can eliminate any of those dominated points as well, which are color coded in white. And now I'm looking at just all the best alternatives the system tells me. Let's take these four alternatives and perform some additional comparison in this case. So I'm going to add those to the basket and switch over to the Compare tab. Now this is what I was talking about. The Results Analytics is the decision support tool, right? So it loads all these in a side-by-side fashion and lets you visualize those. By default, it's going to always compare to say, hey, I think from what you told me, alternative 30 or the configuration 30 is your best point. And I'm going to show you how the other alternatives that you have chosen differ with respect to this best point that I have picked for you, right? So I do have the option to look at the spider chart on the left hand, or the radar plot on the left hand side. So I only have two objectives in this case, so I only see like two of those bars. If I have more, it will expand to show as many of those. The further the point is in this particular chart, the better the values are. So if you look at this, the green color one, which is alternative 30, is really good with respect to delivery time, but with respect to delivery person, but not that great when it comes to average delivery time. The light orange color is the other way around. So we do have the option here to perform a little bit of trade-off to say which of these might work out best for us, right? To do that, we'll move on to the Collaborate tab. So on the top left, if you pay attention in this Collaborate tab, it by default, depending on what we specified, where we did not put any additional weightage on delivery time, just considering the delivery success percent. The system's recommending that alternative 30 is the top choice. Okay? But what if we want to eliminate anything that takes way too longer? Of course, it's going to drain the battery. There's going to be more other problems coming in. Jose's initial simulation of the battery charging and battery charging time and all that comes into picture. So I want to bring in some additional weightage to the average delivery time. As I change that weightage, you see that it immediately changes the ranking and scoring to recommend that what will work out best with this new set of weightage that you have specified. So of course now, with us wanting a little more leeway on the average delivery time, now it has changed that to say alternative 5 will work out better for you, considering you're also interested in a better delivery time than just success percent. Essentially, I mean, in this problem, if you look at it, we just use one hub, but this is going to be distributed across multiple locations, and there could be another hub that handles that one location that 5 is not handling in a much cost-effective and a timely fashion. All right, so this, yes, results analytics kind of lets you perform that trade-off and pick what combination or what alternative works out really well for your set of requirements. Not just that, you also from here can kind of select that alternative that works out best and tag that as the recommended alternative. So I can click that little cup that kind of recommends this alternative as the best alternative. And this is where the true collaboration and history comes in, right? So if you look at the instance table, you pick a particular alternative as that might be your best. There is no history in there to show what kind of trade-off was performed. What is the thought process that went into it to say this is going to be the champion or this is going to be the one that we want to run with? All that information is stored here. All this data is saved for somebody to review and say what kind of trade-off was performed to pick alternative 5 over alternative 30 or any of the other alternatives. Not only that, like you heard in the initial roadmap presentation today, this brings in more collaboration as well. You have the option to write in your comments, put in your comments, collaborate with your colleagues. I've not shown this in this live demo, but this collaborate screen itself, this collaborate widget itself can be loaded in a more interactive and collaborative fashion to work with your teammates to pick which alternative might will meet your requirements pretty well. All right, so to summarize what we saw so far, the systems engineer essentially starts with a set of requirements and inputs that he gets from other stakeholders to develop the system architecture. Meanwhile, design and analysis engineers are building their design model and analysis models. Those models, like we saw in the first half of the presentation, can be tied into your SysML model to validate your SysML model or execute your SysML model. Once you have that executable SysML model, then that can then be tied in using the DOE or optimization to generate different alternatives or different configurations to see how your trade space is. Once you have generated all those trade space points, that can then be loaded into results analytics for you to perform some trade-off and pick which of those meets your targets or meets your needs better. And whatever you learn from there will be then fed back into the architecture, revise the architecture, and as you learn and evolve, you keep improving the system. This, to close it out, what we saw today, or what we saw in the past 1 hour, is enabling system engineer to validate within Cameo using the managed methods that an SME put together. So not leveraging the person's time, leveraging the person's captured process automatically. Easy drag and drop capability for you to integrate that SysML model. Extending the SysML model rather than replicating it, so the SysML model stays true. There is no alteration done to it. And finally, what we looked at was performing trade studies and optimization to quickly run in a parallel fashion, load all that into results analytics, visualize, and pick what your best configuration or alternative is. That's all we had. Thank you.
10 minutes for questions. Any questions?
You mentioned support for reduced order models. Was that simulation at the end using reduced order or the full fidelity tools integration?
It was using a full fidelity. We did not use a reduced order there. But yeah, we do have the capability to generate reduced order models, and those can also be tied back and automated via Process Composer for you to,
Yeah, so that can come back into the workflow in Process Composer.
Yeah, exactly.
Okay, great.
So with all the state machines, were there any physics involved in there, or was it just like, distance equals range times time or something? That's how you were calculating your delivery time and stuff like that?
Yeah, correct. Yeah, for this model, it was a very simplified aerodynamic flight simulation, exactly as you're saying. So we'd have more complex simulations that involve more aerodynamics and actual more specialized models, again, from the SMEs that we can hook into the SysML model. For this one specifically, for the drone, it was just a simplified flight.
Yeah, just curious, for the work that was done in 3D Experience, basically anything outside of Cameo. What additional licenses did you use in this work, or is that something that's resident in 3D Experience?
Yes, so those are, for the first part of it, an SPF license should be good enough to build that simulation process. The second part, where we perform some trade-offs to get the optimization and the DOE adapters, it will be the MDO, or multidisciplinary optimization engineer role. Yeah. All those are readily available roles today in production. Yeah.
For the DOE adapter that you're talking about, is it like, I'm confused whether it's actually running an optimization, like constrained optimization problem, or if it's kind of generating a bunch of different configurations, and then you simulate all of those different configurations and then narrow it down in the results analysis portion.
So when you use the optimization adapter, it is doing that for you automatically. So if you looked at in our results analytic, the first load, it automatically gave, depending on the objectives we specified, to say one of the alternatives was the best alternative. So because I specified that success percent was to be maximized was my only objective, it used that objective to automatically optimize and work towards that.
Right.
Yeah. But when you use a DOE and you don't specify the objectives, it's essentially going to scan through the whole design space or the trade space, and then you would post-process to use results analytics. So it kind of gives you the flexibility to either feed it in at first, let the system run through that, or get the complete trade space, and then you post-process and perform the trade-off there.
Got it. Thank you.
Anybody else?
I understand that you can use it modeling that is outside of what you created in NoMagic, right? So what kind of modeling softwares that you can integrate it with the system? Like a acoustic team, they have their own modeling, performance team. So it is always, for aerospace usage, it is very common that you have your modeling outside of 3DX or no. So that's, I would like to understand if you have it easily integrated, some softwares, and which ones that are.
So when you're talking about model, you were talking about the simulation model? Yeah.
Yes.
So like I talked about, Process Composer is a tool agnostic and has an open data model. So you can happily use the tools that are on the 3D Experience platform, or you could extend and tie in with any of your external in-house tools. There are a couple of ways to tie that. You could just go lazy ad hoc at first to just use a little bit of text parser, OS command adapter. That's what I was doing. There is also the capability for you to write dedicated adapters using SDKs that are published to build a more tightly integrated, more optimally using that software or executing that software kind of a tool set, and then bring that into the process itself.
You don't have like a list of softwares that would be easily integrated?
List of softwares to be easily integrated. List of adapters that can be made available. There are, most of these, because of licensing restrictions and everything, is going to be like Dassault tools. Like you have Abacus, you have CST, Xflow. All those are. There is MATLAB. All those are adapters available that can be made available. That can be shared with you. Sure.
All right. Well, we will release you all to lunch. Thank you very much.
Thank
and
you.
we'll be back in here at 1:30.